Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. Last class we were looking at how to solve some problems with oblique shocks, including cases where we had interaction with a wall. I just realized that I forgot one more extra point. I will start with that and then we will switch to expansions, okay, which will be interaction of one oblique shock with another oblique shock. Okay. Say in some flow field where flow is like this and Mach number is supersonic, I will call it M1, is greater than 1, and the oblique shock is like this. Okay. This is one oblique shock and I will have another oblique shock with another angle, some other angle. I will call this beta 1, 1 will be confusing, let us say I will use A and this is beta B. Okay. I have, let us say I have two oblique shocks coming from say some model here, say there is a wedge here and there is another wedge with higher angle here. Let us say that is how this is created. I am not worried about what is happening to the wedge later, we are just interested in what happens to these two shocks when they meet. Okay. Typically when you go and read books, they will start talking about this one as a right running shock and this one as a left running shock. To understand that, you have to just be the fluid element and just go along this direction. If I go along the fluid direction, what will I see? I am going to see that this shock is starting from, if I am the fluid element standing here, this fluid element is going to see and it is facing this way, right, it is facing the body here, it is going to see that it is starting from the right and going towards the left, this particular shock. So it is called the left running shock, while that one is a right running shock. Okay. It will be, it came from the idea of method of characteristics which we will introduce towards middle of the course, but as of now we will just use that terminology, it is useful for us. Okay. Now we want to know what will happen behind this. For that I have to see what must be satisfied. Okay. I will start, I will remove these beta so that it is not confusing. You know that it is beta A I am talking about, that could be different from beta B. The way I have drawn it, beta B is higher than beta A, which actually means that the deflection of the shock B is more than the deflection of shock A, deflection by shock A. This is what I am having. If I draw the streamline close to the point of intersection, this is going to go like this, while this streamline, this particular velocity vector is going to be turned like this, which means these two flows are going to meet each other at that point. Now the way we think about, we always think about this, I am going to say that it is starting from supersonic, it ends with supersonic. We are still assuming it is all weak oblique shocks, so it is mostly supersonic behind it. So it is a supersonic flow coming here, another supersonic flow coming from the top, and they are colliding with each other. And since the streamlines cannot cross each other, it so happens that each of these streamlines are going to feel the other streamline as a body, which means it cannot go just cross each other like this. So they will deflect in such a way that they will come to a new equilibrium. Okay. They will come to a new equilibrium, and I will draw it in a particular way, we will explain it later. Okay. Oh, I will correct it a little bit, something like this. This is what will happen. Okay. Now let us zoom into this region and draw a separate picture here, much more bigger picture. and I am going to say that this is my beta A and this is my beta B, okay, and this is your right running shock, this is your left running shock. Now I will extend these shocks as if they are going straight without any interaction, and then I will draw these lines with respect to that. Okay. It will do something like this, and we want to start with physical field, right? We always been doing that, so we will start with physical field. What is the overall flow field for this flow here? At this instant, if I say this is extending forever, if you just look at this duct which the flow is seeing, it is looking like this. This is the duct it is seeing. Okay? This angle is less than this angle, which means if I draw a center line for this duct, it is eventually going downward. Okay? Which means these two bodies together want the flow overall to go slightly downward. Okay? So basically it is like we go back to our piston analogy. We always keep switching between piston analogies. It is like I can imagine these two flows as if there is one piston coming from that side, another piston coming from this side, and they are both sending shocks as my piston cylinder is moving this way. Okay. I do not have a flash animation to show this, but it is going to do something like that. Okay. If I do that, then I am going to say this particular piston is moving faster than this one. What does that mean? The shock that is coming here is going to tell, oh, run fast this way. This is going to tell run fast this way, but this fast is more than this, okay, because this is moving much more sharply into the flow. Which means, say I am the person standing in the middle, I am the fluid element going straight along in the center. One side the shock is coming and telling run with 200 meters per second this way. Other shock is telling go 150 meters per second that way. What will I do essentially? I will go with 50 meters per second this way finally. So that is the overall effect. Okay. If I go back to this picture, since we said this angle is more, this is a stronger shock, the deflection more downward is what will eventually happen, and I am going to draw a dashed line here. These dotted lines are just for extension of the shock to tell that the shock moves more upstream in both the cases. We will come back to it after some time. Okay. But this is how it is going to look. Okay. I have drawn this line. This is the final streamline direction after this interaction. Okay. After this interaction, all the flow will have that particular streamline direction. I am just making sure that I am telling only direction and not the vector magnitude. Okay. Vector magnitude will be different for different cases. Okay. We will go and solve such a numerical example later when we also introduce expansion fans, then it is more fun. Then we will say one is an expansion, one is a shock, what will happen, all kinds of combinations we can talk about. We will deal with that after some time. Okay. Currently, I will pick this particular case, and what should be the criterion for finding out how much is the net deflection it is having. Initially the flow was coming straight horizontal, now finally it has deflected down after these two shocks have interacted. What will be that final deflection? Let us say I call it delta. What will decide this is the main thing I am looking at. Okay. If I am finding out what will decide this, if I say beta A is equal to beta B, the whole problem is very symmetric, then my delta will be 0. If this is stronger, then it will push the flow more down, so delta will be more negative. If this beta A is stronger than beta B, that is higher value than beta B, then the delta will be more that side and it will be positive angle. That is what will happen finally. Okay. Now how will I put it in mathematical terms? Okay. What does the flow try and satisfy here? I am saying the flow direction is like this. What does that mean? The streamline here, which is processed by the top two shocks, are going in a particular way, while the bottom shocks are going in a different path, right? They are experiencing different shocks. They are very different shocks, and finally they are coming out to be here. One thing it has to satisfy will be that the streamlines are parallel. That is when the flow will be satisfied. When will I say that the streamlines are parallel? When there is no perpendicular pressure variation. I will write it as gradient in P is 0. Okay. Across that line, which is a special line because it is a boundary between the streamlines that are processed by the top set of shocks versus the bottom set of shocks. Okay. That particular line is a special line. We will give a name for it later, but as of now I am just going to say that the streamlines are supposed to satisfy this particular condition, delta P equal to del P equal to 0. That is the gradient of pressure across that is 0. What will happen if there is any pressure? Let us say this pressure is higher than this, then what will any fluid element do? It will immediately want to go from high pressure to low pressure, that is it will tilt down, okay, which means the streamline will shift till it comes to a point where it is all equal. If it is more pressure on the bottom side, then it will streamline will tilt more up. So it is going to a point where this is the steady condition. We are talking only steady gas dynamics as of now. We are not talking unsteady gas dynamics. We will talk about that towards the end of the course. Okay. So that is one condition. Then what should be the other condition? Okay. Actually velocities are parallel, that is one condition, and pressures must be equal. This is the other condition I am going to look at. Okay. These are the two conditions I will look at. I just gave both are almost the same, it looks like finally. Okay. The way to look at they are different is, if I consider a case where the top fluid which is processed by these two shocks is going some other way, and the bottom fluid which is processed by these two shocks are going say this way, then I will be in trouble. Now there will be a gap created here where there is no fluid passing. That nature does not like ever. Okay. If that is the case, then fluid will immediately go and fill that region, okay, which will automatically adjust this shock. Okay. Everything will naturally take care of itself. So I am going to say the conditions in this kind of problems will be pressures must match and velocity vector direction must match. Those are the two things. We will keep on coming back to these two conditions in gas dynamics. Typically in supersonic flows, we will always talk about vector direction and pressure. These are very important in supersonic flow. We will keep on coming to these two conditions a lot. Okay. These are predominantly applied as boundary conditions in your flow. We do not care about vector magnitude really. Whatever be the velocity, I just have to make sure that the direction is fixed. Okay. Magnitude will affect the energy in the flow, but we are just talking about this currently. Okay. So if I want to solve this problem to find what will be the angle of deflection this way for the new shocks that are after reflection, now I have to go and talk about satisfying these two conditions. How many unknowns do I have in this problem? I have beta C and beta D. Let us say this is my shock C and this is my shock D. I have a beta C and a beta D. So now I have to find those two betas. So I have two unknowns and I have these two conditions. So I will solve for, I have to try it iteratively, try these two values and come to a point where it satisfies these two conditions. Velocity directions must be equal, pressures must be equal across this special line. Okay. That is how we will solve it. We will go and solve it later, but I just want to introduce this phenomenon here itself, so that when you go there it will sink in a little more inside your brain by then. Okay. That is the idea here. Now I will give one more information about this particular line which is dashed line there. The velocities across here and the top and bottom, these two need not be equal. Velocity values need not be equal in our inviscid gas dynamics world. That is, we are assuming there is no viscosity. If that is the case, then the velocity magnitudes can be different. We still have to obey this vector direction must be the same, but the magnitudes can be different. Okay. We will keep it that currently. Okay. If the magnitudes are different, what is that special layer? That particular layer where above is moving say faster and below is going slower, if that is the case, then that particular layer of fluid is called the shear layer, okay, because there is a shear across it. That particular layer is being sheared. Okay. But initially, since we did all inviscid gas dynamics, they gave a name which was slip stream. Okay, that is a streamline across which the fluid elements are slipping. Okay, that fluid element, let us say, is going fast and this is going slow, then these streamlines are going slipping on each other at that boundary. That is why it is called a slip stream. But if I include viscosity, then immediately that changes the name to shear layer, because there is a shear and it will grow like any other shear layer. Like in a jet flow, there will be a shear layer along from the lip, or in a boundary layer flow, there will be a boundary layer which is a shear layer by itself. Okay. It will become a shear layer once I put in viscosity. Okay. You should get used to this name slipstream also. Okay. So if I draw this flow without all these arrows, I will go and draw it again. This is what it will be looking like. The flow comes here, it turns down, and then it turns a little bit. This shock is not very strong. Okay. Comes here, it turns up, and then it turns down very sharply. Okay. So depending on how much the turning should be, okay, this shock strength will change. But I will tell you a quick way to remember this. I can easily tell that if I extend the original shock on this dotted line here and the dotted line there, I know that the reflected shocks will be ahead, more upstream of that dotted line. Okay. A simple heuristic argument or hand waving argument will be that I will take this piston analogy and I will say, when the shock is coming through that piston down straight like this, I will draw that picture also. I have this column, there is one piston, there is another piston, this is going up slowly, this is coming down fast. If that is the case, then there will be a shock coming, this will be fast and this will be going up slowly. This is what will happen. Now, till these two shocks touch each other, they come to the same point, the gas that it is going to go through will be that stationary gas in this world, which will be one initial temperature. But let us consider this particular slow shock. Just after it crosses that shock, it will still keep going. It sees more fluid, it will keep on going and telling all the way till the end. Okay. Now, when it is going, crossing that shock and going past, it is going to see the new gas which is heated by the shock. So it is going to travel faster in the perpendicular direction, right? It is going to go faster that way. While this one is also going to travel faster this way, but not as fast as that change. Okay. Now imagine this whole thing happening here while I move this cylinder this way. That becomes our piston analogy from 2D to 1D, right? So if I do that as this is moving, then I will go to this particular case where the stronger shock gets to go past this weaker shock heated gas, which means it will not be very strong after the shock interaction. So it will just go a little forward. While the other one, the weak shock, is going to go after this point into a strong shock heated gas. So it will deflect more that way. The idea of these shocks are, this weak shock is your left running shock, while the stronger oblique shock is your right running shock. Okay. So the right running shock will just go straight and cross that point and just keep going this way, while the left running shock will go like this and go like that. If in case I have a wall somewhere here and this shock goes and hits there, now whatever we did last class will come in. Okay. The whole thing of this sees the flow that is going in a particular direction and then it is turning and then it has to turn to that particular wall, all that will happen out there. Okay. But we are currently looking at only this region, only the local region. Ideally in gas dynamics, all we do is we will just break down the problem into small bits we have already experienced, okay, and then we will put them all together. If I currently pick a very complex problem, let us say I have a body like this in supersonic flow. and ideally I should not be drawing this beyond this point because I haven't taught you enough to go past this point. Okay. But if this is the case, when the flow comes in, let us say it is a 2D object like a wedge, then it is going to see that this is a very small angle, it will have an attached shock, it is going to go like this, other side let us say is parallel to the flow direction, so there is nothing there. Same thing happens here. And now when these shocks come in, whatever we did here will happen, all that will happen. After that, now I have to think about interaction of this shock with this wall, it will bounce off and come back, this will go bounce off and come back. Now this will keep on oscillating like this several times. This is what they start calling shock trains inside. Okay. We will go deal with this kind of intake problems later. Currently we will jump to some other problem after this. Okay. Another problem I can think about is, what if this reflection across here for this particular angle change happens to be a detached shock. That is the next case. I am going to a case where I am saying this is the shock deflection from the original shock, I have another shock, this is the deflection. When they come and meet, they have to, let us assume we have symmetric shocks, easier to work with, okay. And then I am saying it has to turn back, but the Mach numbers have decreased after the first shock. When that happens, it is going to go to a point where this particular theta is crossing the theta critical, the change in angle, right. How do we look at this as an oblique shock problem? I will block this particular part like what we did last class. The flow is coming, flow is supposed to come parallel to the streamline, like what we did last class, right. I will draw a line like this, the flow is coming along this paper and then turning to that direction. If that is the case, then there will be an oblique shock sitting somewhere there. Okay. But if we find that that deflection angle is more than the critical angle for this approaching Mach number, then there should be a detached shock sitting here. But there is nothing to detach from, there is no real solid object there. And the same, since I said it is a symmetric problem, the same thing is happening here. Now what did we do last time? We erased this shock a little further and then put a normal shock. I will do the same thing here. So it will look something like this. I will draw a better picture. It will look something like this shock and this shock, if they have to turn back straight here, if they find that this Mach number is not very strong, say these Mach numbers are not very strong, any one of them if it is not very strong, it will end up with this condition. Okay. And after that, it will have a normal shock in the center, flow that is coming inside this region will just face a normal shock and it will go this way, and there will be two slip streams this time. Two slip streams, and they need not go parallel to each other. Okay, I just drawn it such that it is converging, most likely it will converge. Okay. We will keep it like this for now. Okay. The flow comes here, turns down, and then this is going to turn it out to parallel to that slip stream there. And here the flow comes here, turns in, and locally it is going to turn it to parallel to that slip stream there. This is what will happen in the flow. Okay. This is just a more complex example of what two shocks can do. Okay. With this we will stop oblique shocks for now. Later we will go and start solving flow field in different flow situations. Okay. Individual problems we will take and solve it, but currently we will switch over to expansion waves in compressible flow. Okay. When we go to expansion waves in compressible flow, it is not exactly a straight opposite equivalent of a shock in a compression world. Okay. Shock causes compression, expansion is the straight opposite. I cannot tell that, it is a very thin strong discontinuity in the expansion. Why? We already proved this in when we were deriving normal shocks. We said that if I have a strong discontinuity, if I have P2 by P1 more than 1, then my delta S is greater than 0. I will just remind you of that case. delta S by R versus, it was P2 by P1 I think. If I have something like this is your 1, okay, and this is less than 1, this is more than 1. If I have this case, you had a curve that was like this. Okay. I showed this plot sometime back, maybe we will think about it in the video. Okay. I have this kind of plot. This particular plot, if I look at P2 by P1 more than 1, delta S is positive, which means it will occur. Okay. When P2 by P1 is less than 1, which is our expansion, it so happens that delta S is negative. When that happens, then that is not naturally possible. Okay. This is what we said that time itself, and we said only compression shocks are possible. Okay. So I am going to use that statement, compression shocks are the only ones that are possible. But I also gave a caution statement there saying this is for our kind of gas, air, and most of the common gases will follow this type of a curve. There are special gases, I gave the name all that time also, BZT gases. Okay. This special gas which will have this curve inverted, that is, it will go the other way, where only expansion shocks are possible, compression shocks are not possible. Okay. But most common gases do not have this property. So we will not talk about it in our simple gas dynamics world. Okay. So that caution being given, now I know one extra statement from before, which is expansion shocks are not possible. Okay. Now I have to tell you one more thing which I will introduce later, but it is a right time to introduce, so I will introduce it right here and then I will talk about it in detail later. When I say there is a compression shock, I am going to call it as, it is a whole bunch of compression waves come together and form a very thin layer, they are all one on top of each other. Okay. When it is expansion wave, that is not the case. Okay. Expansions, if I say there is an expansion shock possible, even that will be doing exactly the same thing. But it so happens that expansion waves cannot accelerate to go and sit on top of each other. We will see why after we do some expansion analysis. Okay. So now the way to think about it, I will have a set of expansion waves, let us say, in my flow. It will not coalesce to form an expansion shock, but if I send a whole bunch of compression waves into my flow, they will all coalesce together to form one thin layer called compression shock, which is what we have been doing all this time, normal shock, let us say. Okay. So the way to look at it, I am going to consider expansion as happening over a big region in the flow. What is a typical example for an expansion? I have a box and I am going to, let us say, open this portion suddenly. This is having high pressure, outside is, let us say, very low pressure. What is going to happen? Our stadium example, there are so many people inside stadium, the gate is open and there is empty space here. What will happen? People will run out, they do not want to be sitting in the crowd. So when they come out, the people sitting next will realize there is more empty space, so they will start moving this way, everybody will start moving this way, while the information that the gate is open goes that way. Okay, this is your expansion wave. Expansion goes that way while the velocity goes this way. Okay, mass goes this way while the expansion wave goes that way. That is what you have to remember. Previously we said compression wave where there is more people dumped into the stadium and closed. Then they have to readjust, so there will be a compression wave going, all the people will go that way along with the compression wave. Expansion, if the wave goes to the right, the velocity induced by the wave is to the left. Okay. We already did this, I just want to reiterate it several times so it is easier for you to remember all this. Okay. Now let us go look at one particular wave like this. Okay. Oh, actually I want to tell one more point here. If I open up like this, the very first time the streamline, the particles that are sitting at the edge will see that there is a huge pressure change. Okay. So it will send a very strong expansion wave, strong in a sense it will tell that the pressure jump is very high, that is all it will tell. The information that is going in is going to tell you can accelerate very fast this way. But when it goes to the next fluid element here, this fluid element has already moved out because there is velocity now. Now this region is not as low a pressure as before, it is slightly higher. So what will happen? The next fluid element that is coming here and seeing this is going to tell the pressure is not as low as what the previous wave was telling, but it is still less. So the very first wave will tell that the pressure difference is very high, and after that every wave is going to tell that the pressure difference is slightly lesser, slightly lesser, slightly lesser, and there will be a whole bunch of such waves going into this flow. Okay. So if I draw that again here, then I am going to tell, if I open this edge and wait for say a few seconds, then I will tell that the first wave will be here and the last wave will be the current wave which is being created. The whole region, there are so many waves here. Okay. That is what will happen. If I draw, let us say I draw, this is my location and this is my pressure. If I plot along inside this box, then initially at time t equal to 0 it was all constant pressure. Pardon my axis, it should be all straight. Now because I dropped this pressure to some very low value, let us say this value, the outside world is this value, so it is going to go for something like this. With time it is going to do something like this. Okay. It will do something like this. With time the region where the pressure is constant will keep on decreasing. The very first change is very strong, if you notice, the pressure is dropping very fast. After that it is dropping slower and slower and slower, and at this point it is dropping very little. The very first wave was very strong, after that it is all lesser and lesser waves, less strength waves. P2 by P1 across the wave will be slightly lesser. The delta P will be slightly lesser, that is the best way to put it. Okay. That is what you will see. Okay. That is the physical feel for things. Now we will just go and put this in equations form, just one simple expression I want to get, and then we will talk a little more. Let us say I will go to a condition where I have only one expansion wave and it is wave fixed coordinates. So this is a stationary wave sitting there. I am going to say there is flow with velocity u1 into it this way, with pressure P1, density rho 1 and temperature T1. On the other side, I am going to say, since it is a very thin wave, there will be a small change. Let us just put arbitrarily u1 plus du. If du is positive, then velocity increased. If du is negative, velocity decreased. We will just keep it as some variable. Okay. And then this will be P1 plus dp, rho 1 plus d rho, and T1 plus dt. All this will happen. Now let us do this mass conservation across this. Okay. Mass conservation is, I am going to pick a control volume across this wave and I will make it equal area, constant area control volume. So I will just have rho 1 u1 equal to this density into this velocity. Okay. Now of course I can expand this, rho 1 u1 will cancel with this rho 1 u1, and I will neglect the du d rho term because it is two very small numbers multiplied by each other. So the remaining things will be 0 equal to rho 1 du plus u1 d rho. This is all I will have, or I will rearrange this expression, d rho by rho equal to minus du by u1. Similar thing we derived when we were doing speed of sound derivation. I am just telling you where it is coming up. Okay. Now one of the important things I have to note here is I am going to have a condition, if my density decreases, my velocity will increase. That is, if d rho is less than 0, then this will be more than 0, du will be more than 0. Or vice versa after that. Okay. Which means if I have an expansion which is d rho, expansion is density decreasing. So, d rho is less than 1, which is the condition we are looking at, d rho less than 0. Okay. If it is expansion, then density decreases. If that is the case, du is positive. So, I will go back and look at this now. Okay. I am going to say if this is an expansion wave, I did not put an expansion there. If this is an expansion wave, then du is positive, d rho is negative. That is what you are seeing, which means my expansion wave accelerates the flow if I am sitting on the wave itself. If I am on shock fixed coordinates in steady world, then I am going to have velocity increasing across this wave. Okay. I will keep on telling this because now we will go and do the other reference frame where I am outside reference frame, lab reference frame or the board reference frame if you want, and then we will study if the wave is also travelling, what will happen. That is a more complex problem, we will not deal with it fully, we will just use that piston argument or stadium argument if you want, that is an easier thing to use. Okay. Now the next thing, I do not want to go through the same derivation as we did in the speed of sound argument, speed of sound derivation, but it is going to be almost the same. So, if I use my momentum equation along with mass equation, I will end up with a case where I will get to dp by d rho is equal to a square. But I cannot say this to be equal to a square directly, okay. It is just supposed to be equal to the wave speed, that is all I can tell from the similar arguments as what I did for speed of sound, that is some, I believe it was class 8 or class 9, somewhere there. Okay. Anyways, so if I do that, I have to be proving that my changes are very small. We gave the argument in speed of sound derivation that my wave does not change anything in the flow, it does not change pressure, it does not change density, it does not change velocity, it does not change anything, then it is my sound wave. Okay. And that is the particular wave which will travel with speed of sound really. But this is not really a wave which does not change anything, it actually changes the velocity, pressure, density, temperature, everything. If it is changing, can I still use that argument? We are going to use that argument. Okay. What is the justification I am giving for it? I am going to say since it is one single wave out of a whole bunch of waves, I am going to say this particular wave is going to change only by a small bit, and there are innumerous waves. This we will typically represent it by 5 or 6 lines as a wave, but a bunch of waves, but actually there is infinite number of waves inside that band, that is what it is really. Okay. So, each wave individually will change it by a very small amount, but overall effect will be the integral effect, which will be a big number, that is what it is. I am going to use that argument and say the change caused by this wave is almost 0, the du, d rho, dt, dp, whatever we had in the last board, everything is almost 0, that is what I am going to say. If it is almost 0, then I am going to say this is dp by d rho is almost equal to speed of sound, because the expansion wave moves or behaves as if it is a sound wave, almost a sound wave. So, it will travel with almost the same velocity. Okay. That is the argument I am going to use. Okay. And which means it is almost isentropic. Okay. We are going to say that it is almost behaving like sound wave, so it is almost isentropic wave. But when in using expressions, we will directly go and say it is isentropic. It is not really isentropic. In reality, a single compression wave will travel slightly faster than speed of sound, and a single expansion wave will slightly travel less than speed of sound. Okay. But it's very difficult for us to find the difference between these two values. So we'll just use this number. For engineering it will work good, okay, unless there is a very serious research problem where you need to have that kind of resolution, it shouldn't affect us. Typically it will not affect us for any of the problems, okay. Now let us look at it from the point of view of a shock, a wave that is moving. It is not a shock, it is actually just an expansion wave, okay. This came from speed of sound derivation. I did not want to derive the same thing again, just go back to that lecture notes and you will see it, okay. Now I will go to another reference frame where I have a wave that is moving, okay, a wave that is moving and velocity is 0 here. What will happen here? This will be u prime equal to 0 plus du p1 u1, I will put u1 will be 0 here, fine, rho 1 t1 p1 plus dp rho 1 plus d rho t1 plus dt, same thing, except for now I am going to call this the expansion wave, single expansion wave, not a whole bunch of them, just one wave, okay. Now I want to look at it in this coordinate system, okay. Even in this coordinate system we should have but it's very difficult to use mass conservation here because my control volume should be moving with the wave. So to analyze this problem I am going to transform this to my wave fixed coordinate system, okay. I will transform it and come back to it, okay, just a minute, we will come back to this again. I will transform this. So how will I transform this? This is my velocity, let us say is a, it will be exactly a if u1 is 0, okay. So if this is a, then I will impose a velocity to the left everywhere in all the velocity fields. So my u1 will be equal to minus a, and here u1 prime, actually not u1 prime, u prime equal to minus a plus du, and all the pressure, density, temperature will just be varying by dp, d rho, dt, that does not change anywhere, only velocity field changes with change in coordinate system, okay. So if this is the case, now we have already solved this problem. If I put a control volume across this and I am going to say, since it is minus a in this direction, it is equivalent to having a in this direction and it is going with a minus du this way. This is what I have. But we already have this kind of result and I know that this is an expansion wave. In an expansion wave, if a flow crosses it, its velocity increases, that is what I know. So I know that a minus du is greater than a, which actually means that du is less than 0, right, just immediate result from there. Now I will switch back from this transformation back to the original coordinate system where I am saying I am fixed to the wall here outside reference frame, but I have this value du, difference in velocity does not depend on reference frame switch. So I will just put the same du here, du is less than 0, which means now initially I am having the convention that velocity this way is positive, right. If du is less than 0, I will put that in here, u prime is less than 0, which means I am having a flow actually with u1 equal to 0, I am having a wave travelling this way with a. What I am finding is there is a velocity induced this way finally because u prime is less than 0. Now I am using that convention and now I will just put magnitude here. The direction is already taken care of with this minus less than 0, okay. So this is what we were talking about at the beginning when we introduced the expansion wave, right. When there is one wave going this way, it is telling that there is lesser pressure here, move this side, and that is the induced velocity this side. This is what you are seeing. I can of course do the whole explanation with u1 not equal to 0. If it is not equal to 0, then I have to find the relative velocity between this and then use that to move from across this reference frame to here, okay, which I believe you can do by yourself. You will still find that the velocity induced by expansion wave will be to the backward direction. Okay. Now I will just think of expansion waves as some person who is running, then it is going to tell the fluid which it is just now contacting that go to where I am coming from. That is the information it is telling. While in contrast, the shock is going to tell the opposite, come along with me is what it will tell. Okay. They are going to tell opposite information. If you think about this, it becomes easier later when the problem becomes more complex. Now, typically people encounter these expansions in 2D flows much more than just simple 1D flows. Most of the flows are 2D anyway, but we will consider 2D problems because that is simple gas dynamics. Okay, we will come back to 1D expansion later. If there is a supersonic flow going like this, okay, previously when we did shocks, we remembered this basic flow shape. Last class I told you, right? This is your deflection of the wall is into the flow field. Flow is coming like this, the wall moves into the flow sees as an obstruction, and this becomes a compression wave, and the whole bunch of compression waves come together to form a shock. In contrast, now I am going to make you remember this other flow field, other basic shape, a theta deflection away from the flow direction. If the flow was just going straight, it will see that there is a huge gap here. This is why it wants to expand. If I think about it that way, now the expansion set of expansion waves must start from this corner. Why? This is where the change occurs. It is as if there is a whole bunch of people walking straight like this, and suddenly the road becomes wider. What will they do? They will slowly start filling the place. Who will see it first? The person in the corner will see it first. They will walk like this first, okay, and they still want to travel in this way, so they will travel a little faster this way. And once this last person moves, the next guy sees that there is more gap next to him, so he will travel faster. The whole sequence goes, and they will be having slight delay. The person here will see this change only after he has traveled some more, when the person next to him has moved down. Okay. If I imagine that analogy, the region where the change starts to happen will be along some line like this, okay, and there will be one line where it will tell this is the final change, there is no more change possible. That line will be somewhere like this. Okay. There will be two lines, start of expansion, end of expansion. Okay. Now, after this whole thing, the flow turns this way, and since we already did this in 1D, that after the expansion is experienced, the flow accelerates, I can actually put that these velocity vectors are shorter than these velocity vectors. I can give that already here. Okay. We will keep it that way. Okay. Now, ideally, what we have to do is find expressions for a given theta. What will be the change in Mach number, what will be the change in pressure, what will be the change in temperature, density, everything across this expansion wave, set of expansion waves. Now we will give a nice name for this, okay, since it looks like the fan, the fan which opens up like this and they use it, right, that kind of fan, they call this expansion fan. Okay. This is the expansion fan. If you want the Japanese paper fan, it is something like that. That is why it is called the expansion fan. Okay. We will go deal with more of this, but I will just do one more thing since we have only few seconds. Okay. The very first wave that is going like this, the speed at which it will go in will be almost equal to sonic line, right. Every wave is going to do that exact thing. The very first wave is going to move with the speed of sound of this gas, the gas that is approaching. Okay. That is what will happen, which means I am going to have this line having an angle equal to Mach angle of the incoming gas. I will put mu 1. Okay. And by similar arguments, I can tell that the last wave, if I call this as region 2 and this is region 1, the last wave will have, with respect to streamline, this angle mu 2. Okay. And this very important point, it is with respect to streamline always mu. Okay. We will go try and find expressions for the final angle, final Mach number with respect to the theta. Okay. We will try and get it there. We will start with that derivation next class, and we will probably go into explaining more things after that. That will probably one more class of expansion fan, then we will move on to more practical flows. Okay. Then we will see you people next class.